Hello everyone, welcome back to this online class. Today we are going to look at how to solve non-homogeneous linear ODEs of the second order. In particular, we are going to look at the inverse differential operators method. We are given this question. We are asked to solve the following differential equations. In part A, we have d squared y over dx squared plus 2 dy over dx plus y is equals to sine x cos 2x. Part B, we have d squared y over dx squared minus 2 dy over dx plus 4y is equals to cosine squared of x over 2. And part C, we have d squared y over dx squared plus dy over dx is equals to x times cos x. So first of all, we need to write those problems in terms of the D operator. So this is how we define our D operator. We say let D be derivative with respect to x, so that where we have d squared is the same as the second derivative with respect to x twice. So let's start with part A. Write the ODE in terms of the D operator. That is part A. In terms of the D operator, it will be d squared plus 2d plus 1. The whole of this is operating on y to give us sine x times cosine of 2x. So this is a non-homogeneous ODE. It has two solutions. The first one is the complementary function, and the second solution is the particular integral. So let's start by finding the complementary function, which denote by y subscript c of x. So for us to get this solution, we need to solve the homogeneous part of this equation. Let's call it equation star. Homogeneous part of that equation is d squared plus 2d plus 1 operating on y to give us 0 when the right hand side is 0. So the auxiliary equation equate the coefficient of y to 0, so that will give us d squared plus 2d plus 1 is equals to 0. If you factorize, you're going to get d plus 1 squared is equals to 0. So from here, we can find the roots. Remember, there are two. d1 is equals to d2, and so that is negative 1. These are case of real and equal roots. Real and equal. So how do we write our solution when the roots are real and equal? So you can just say here that therefore y subscript c of x is equals to a constant c1 times x plus another constant c2. This should multiply exponential negative x. So that's the complementary function. Let's find the particular integral, the second solution. Particular integral. Remember, we are using the inverse D operators method. So yp of x, how do we get it? You need to make y the subject in equation star. So you're going to divide by the coefficient of y in that equation star, so that we'll have 1 over d squared plus 2d plus 1. This should operate on sine x times cosine of 2x. This is a product of sine and cosine. How do you operate on that? That's the question. So let me comment on this function that you need to operate on. That this is a case where you have product of sines and cosine. For us to be able to operate on that kind of a product, what you need to do is this one. We use trigonometric identities. I want us to recall that sine A plus B is the same as sine A cos B plus cos A sine B. We also know that sine of A minus B is the same as sine A cos B minus cosine of A sine of B. So I need sine A times cos B. I need to make that the subject. So what I'm going to do here is to add these two equations. If I add them, what will I get? I'm going to get sine A plus B plus sine A minus B is equals to twice sine A cos B. So therefore, where we have sine A cos B is the same as 1 over 2 times sine of their sum A plus B, then plus sine of the difference, that's sine A minus B. So this is what we use to be able to express sine A cos B in terms of sines of multiples of those angles. So if I put A is equals to X, because this is our A, and our B is equals to 2X, so what will you get as sine X cos 2X? So therefore, sine X cos 2X is the same as 1 over 2 sine of X plus 2X plus sine of X minus 2X, which is the same as 1 over 2 times sine 3X plus sine of negative X. But remember, sine is an odd function. So sine of negative X is the same as negative sine X. So this can as well be written as 1 over 2 sine of 3X minus sine of X. So that's what I'll replace here. So our YP is now the same as 1 over d squared plus 2d plus 1. Our function is now 1 over 2 sine 3x minus 1 over 2 sine x. That's the function that we operate on. And so these are two terms, so we can split that inverse d operator so that you can operate on each and every function. So this you can as well write as 1 over d squared plus 2d plus 1 operating on 1 over 2 sine 3x, then minus 1 over d squared plus 2d plus 1 operating on 1 over 2 sine x. So that what do we get here? Let me separate this. Now let's see. In the first case, our alpha is 3. In the other case, our alpha is 1. So alpha is equals to 3 in the first case. The other one, alpha is equals to 1. Here it is equals to 3. So replace d squared by negative alpha squared. That's the hint. We replace d squared by negative of alpha squared. So that in the first case, we'll have, of course, negative alpha squared in the first case is negative 9. So we'll have 1 over negative 9 plus 2d plus 1 times 1 over 2 sine 3x. The other one is minus 1 over alpha is 1. So alpha squared is 1, and so negative alpha squared is negative 1. So this negative 1 plus 2d plus 1 operating on 1 over 2 sine x. If I simplify, what do I get? That's the same as 1 over 2. Here we have 1 over 2d minus 8, then sine 3x. The other one is negative 1 over 2 times 1 over 2d. Of course, negative 1 and 1 will cancel. Then we have here sine x. So you can as well write this as 1 over 2 into 2d plus 8 over 2d minus 8 times 2d plus 8, operating on sine of 3x, then minus 1 over 2, of course it's now 1 over 4, so what I can see there's another 2 in the denominator, so minus 1 over 4 d inverse of sine x. That's what we have, and d inverse means integral operator. So this is the same as 1 over 2, 2d plus 8, denominator is difference of 2 squares, that's 4d squared minus 16. Then here we have sine 3x, then minus 1 over 4. When you integrate sine x with respect to x, from 0 to x, what do we get? What did we differentiate to get sine? It was negative cosine, so negative cos x gives you sine x when you differentiate it. So here, in the first term, again, the alpha is 3. Replace d squared, by negative alpha squared. So where there's d squared, I'm going to put negative 9. Negative 9. That should be negative 9. Where there's d squared. So what do we have? 4 times negative 9 times minus 16. That is negative 36 minus 16. You can press that. What should it give us? Negative 36 minus 16, that's negative 52. Times 2, that should be negative 104. So what we have here is negative 1 over 104 2d plus 8 sine 3x. That's now a plus 1 over 4 cos x. And so the d that we have there now means derivative. So we'll have negative 1 over 104 2 times derivative of sine 3x plus 8 sine 3x, then plus 1 over 4 cosine of x. And so if I simplify this, I'm going to get negative 1 over 104 Now, derivative of sine 3x is the same as 3 cos 3x. So this will give us 6 cos 3x plus 8 sine 3x, then plus 1 over 4 cos x. So that is the particular integral. Of course, you can simplify that. You can be able to open the bracket so that you can simplify that further. Now, we have the two solutions. How do you get your general solution? You simply add those two solutions. And so what we'll get here is the sum of those two solutions, the complementary function plus the particular integral. So before we look at the general solution, let's see where we had 1 over 4. There's something that we need to correct. Remember, 8 squared is 64, not 16. So there's a correction here. We didn't realize this. It was 8 squared is 64. So here it is 64. So that we'll have now, instead of 1 over 4, because here is 4 times negative 9, that is negative 36 minus 16, that is negative 100, then times 2, negative 200. So where we have 1 over 4, those will change to 200. So this is 200. Even the other one is 200. There's a slight correction. And even here it is 200. So I'll change it. This is 200. Even here it is 200. So where we have 1 over 4, we have said that is changing to 200 because there's a problem when you are squaring the 8. So you write here general solution. General solution is equals to complementary function plus the particular integral. You can say, or y is equals to yc plus yp. And what is our yc? We can replace each of them. You can say here, or y, let me use another color. Y is equals to, our yc was c1x plus c2 exponential negative x minus 1 over 200. Here we have 6 cos 3x plus 8 sine 3x, then plus 1 over 4 cosine of x. So that is the general solution of the ODE in part A. Of course, C1 and C2 are arbitrary constants. So let me bracket this solution. That's the solution for part A. Let's solve part B. Again, write the ODE in terms of the D operator. So let me check it. That equation is, in terms of the D operator, is this one. That is d squared minus 2d plus 4, everything operating on y to give us cosine squared of x over 2. So we write it here, down here. We have d squared minus 2d plus 4 operating on y to give us cosine squared of x over 2. Again, here we expect to have two solutions. The first one is the complementary function, which we denote by y subscript c of x. So we need to solve the homogeneous part of this equation. Solve, our homogeneous part is now d squared minus 2d plus 4, operating on y to give us 0. So what is the auxiliary equation? Right here, auxiliary equation, I can use another color. Our auxiliary equation is d squared minus 2d plus 4 is equals to 0. So let's find the roots of this equation. Of course, it is quadratic in the d operator. So there are two roots. We use quadratic formula. So d1 and d2 is negative of negative 2. So that's 2 plus or minus the square root of negative 2 squared minus 4 times a, which is 1 times c, which is 4. Everything over 2 times a, which is 1. So that's 2 plus or minus. Inside the square root, we'll have 4 minus 16. That's negative 12. So that's the square root of negative 12 over 2. And this is the same as 2 plus or minus iota times 2 root 12. Iota times root 12. That's root 12 over 2. What is root 12? Root 12 is the same as root of 4 times root of 3. That is 2 root 3. So instead of root 12 here, I'll just write this as 2 root 3. 2 root 3. 2 root 3. So this is the same as, if I divide by 2, is the same as 1 plus or minus iota times root 3. Iota is the square root of negative 1. So you can take note that what we call iota is the square root of negative 1. So these are complex conjugate roots. So comment on this one, you write complex conjugates. When the roots are complex conjugates, how do you write your general solution? So you write therefore yc of x is equals to exponential x. That's exponential alpha x. Alpha is 1 here. This other one is beta. So this is alpha. This is beta. Then we have c1 cos beta x. That's root 3 times x. Plus c2 sine beta x. Beta is root 3. Then times x. That is the complementary function. Let's see how to find the particular integral. So Roman 2, you write particular integral. And this is denoted by y subscript p of x. That's our particular integral. We are using the inverse d operator. So I have to make y the subject of the formula. In the ODE in part B, make y the subject of the formula here. So that we'll have 1 over d squared minus 2d plus 4 operating on cosine squared of x over 2. So we write this as 1 over d squared minus 2d plus 4 operating on cosine squared of x over 2. Look at this one. Cosine squared of x over 2 is a product of cosine and another cosine. This is a product of cosines. We need to break it down to maybe cosine of multiples of x. So I used the trigonometric identity. Take note that cos A plus B is equals to cos A cos B minus sin A sin B. Cos A minus B is equals to cos A cos B plus sin A sin B. So if I want cos A times cos B, because product of cosines only, I need to add these two identities. So let me add them. I'm going to get cos A plus B plus cosine of A minus B is equals to 2 cos A cos B. So I can make cos A cos B the subject, so you can say that therefore cos A times cos B is the same as 1 over 2, that's 1 over 2 into cos A plus B plus cos A minus B. That's the identity. So what of cosine squared of x over 2? A is equals to B and is equals to x over 2. So we now put A is equals to B, which is equals to x over 2. So we are going to get cos squared of x over 2 is equals to 1 over 2 cos x over 2 plus x over 2 plus cos x over 2 minus x over 2. And so this is the same as 1 over 2 into cosine, that's x over 2 plus x over 2, that's x, then plus cosine of 0. Remember cosine 0 is 1, so this is the same as 1 over 2 cos x, then plus 1. Simply half into 1 plus cos x. So that's what you need to replace with the cos squared of x over 2. So let's go back to our particular integral. Instead of what we have there, so this can be written as 1 over d squared minus 2d plus 4. Then here we have 1 over 2 into 1 plus cos x. That's what we have. And this can be written as, this is the same as 1 over d squared minus 2d plus 4 operating on 1 over 2, then plus 1 over d squared minus 2d plus 4 operating on 1 over 2 cos x. Those are two different terms. So let's see, the first term is a polynomial of degree 0. This is a constant term is a polynomial of degree 0. And so we drop the higher powers of d that are greater than the degree of the polynomial. Drop the powers of d which are greater than the degree of the polynomial. So we drop d squared and negative 2d. We remain with just 4. So this means we'll have 1 over 4 times 1 over 2. Somebody might be asking, why are we dropping d squared and the negative 2d, because in the d squared, the power there is 2. 2 is greater than the degree of the polynomial. Remember, our polynomial is of degree 0. So 2 is greater than 0. And also, why did we drop negative 2d? Negative 2d, the power of d there is 1. 1 is greater than 0. So we drop those two terms. And so we remain with the 4 in the denominator. So we have 1 over 4 times 1 over 2. What about the second term? Here, plus, look at here, we now operate on cosine of x. Cosine of x is the same as cosine of 1x, so that our alpha is equals to 1. So alpha squared is 1, and so negative alpha squared is negative 1. So put where there's d squared is the same as negative 1. So this is the same as writing 1 over negative 1 minus 2d plus 4 operating on 1 over 2 cos x. That is what we have. Let's simplify. It's the same as 1 over 8, then plus 1 over 2 times 1 over negative 1 plus 4, that's 3. So 3 minus 2d. Here we have cosine of x. I still need to replace the d squared in the denominator, which I don't have d squared in the denominator, but we can introduce it. So multiply the numerator and denominator by the conjugate of the denominator. So this can be written as 1 over 8 plus 1 over 2 into 3 plus 2d over 3 plus 2d times 3 minus 2d cos x. So that this you can write as 1 over 8 plus 1 over 2. Then in the numerator we have 3 plus 2d. Denominator we have difference of two squares. That is the same as 9 minus 4d squared. So this is 9 minus 4d squared operating on cosine of x. So where there is d squared, you put negative 1. So put where we have d squared, that's the same as negative 1. So what we'll have is 1 over 8 plus 1 over 2. Now we have 3 plus 2d over 9 minus 4 times negative 1 cos x. And so this you can as well write as 1 over 8. 9 minus 4 times negative 1, that's 9 plus 4, which is 13, times 2 is 26. So plus 1 over 26. 3 plus 2d cos x. When you take it inside, you get 1 over 8 plus 1 over 26, 3 cos x. The other one is 2 times derivative of cos x. That would be minus 2 sine x. So that is our particular integral. Now we need to find the general solution. You simply add those two solutions, the complementary function and the particular integral. So you can write here that the general solution is equals to complementary function plus the particular integral, or y is equals to yc plus yp, or y is equals to, let's see what we got as our complementary function. We refer to it, that was exponential x, c1 cosine of root 3x plus c2 sine of root 3x. That's what I write here. I write here exponential x c1 cosine of root 3x plus c2 sine of root 3x plus now the particular integral. We have found 1 over 8 plus 1 over 26 times 3 cos x minus 2 sine x. So that's our solution, the general solution. And in this case, C1 and C2 are arbitrary constants. So that's the solution in part B. As you can see, you'll have to use trigonometric functions to be able to break down the given functions. So let's answer part C. Of course, we need to write the given ODE in terms of the D operator. So let's check the ODE in part C. I'll take you up all the way up to part C. It's up here. So this is the question. Now, when you write this in terms of the D operator, we'll have D squared plus D operating on Y to give us X cos X. So we go back. That is D squared plus D operating on Y to give us X cos X. I'll write it here. D squared plus D operating on Y to give us X cos X. We have two solutions. The first one is the complementary function. This is denoted by y subscript c of x. And how do we obtain it? You solve the homogeneous part of that ODE, that is d squared plus d operating on y to give us 0. So that the auxiliary equation, you need to equate the coefficient of y to 0, so that is d squared plus d is equals to 0, which can also be written as d into d plus 1 is equals to 0. So let's find the roots. There are two roots. The first one is 0, and the other root, the second root, is negative 1. So 0 and negative 1 are real numbers, and they are distinct. So this is a case where we have the real and distinct roots. Real and distinct roots. So how do we write our general solution when the roots are real and distinct? So we'll have yc of x is equals to an arbitrary constant c1 exponential 0x plus another constant c2 exponential negative x. And you know anything raised to 0 is 1. So this can as well be written as C1 plus C2 exponential negative x, where C1 and C2 are arbitrary constants. Let's get the other solution, particular integral. So right here, Roman 2, particular integral. This is denoted by y substitute p of x. And how do we get it? You need to make y the subject of the formula in that of ODE in part C. So we divide by d squared plus d. So write 1 over d squared plus d. This should operate on x cos x. The question is, how do you operate on a product of a polynomial and a trigonometric function? So let me comment on this function. This function here is a product of a polynomial and trigonometric. Cosine. When you have such a case, you need to use exponential shift rule for you to operate on such kind of a product. So we are saying use exponential shift rule. But you see, you cannot see the exponential function in that product. So we have to rewrite cosine of x as an exponential function so that we can be able to use the shift rule. So recall, take note of the Euler's identity. Euler's identity that when we talk of exponential ix is the same as cos x plus I sine x. So that the cos x is the real part of that complex number. This is the real part. Sine x is the imaginary part. So this is imaginary part. So if I replace cos x by exponential ix, it means that my particular integral will be the real part of my solution. So I want to replace cos x by exponential ix so that our answer here should be the real part of the solution of this one, 1 over d squared plus d operating on x exponential iota x. RE there means real part. So let's work out the bracket. Then once we have found our final answer, we extract the real part. So now you can write now 1 over d squared plus d operating on x exponential iota x. If we shift the exponential function to the left of the inverse d operator, we'll have, remember alpha here, alpha is equals to iota I. the coefficient of x. So that where there is d, you replace by d plus alpha. So this is the same as exponential iota x. Then now the d operator becomes 1 over d plus I, because d plus alpha, our alpha is I, this is squared, plus another d plus I. Now we remain with x as the function there. So let's open up the denominator. Take note that when I open up the denominator, we are going to get exponential ix times 1 over d squared plus I2d plus I squared, which is -1. Let's just write plus I squared. Then plus d plus I. This will operate on x. So if I simplify that further, remember I squared is -1, so you can say put I squared to be equal to -1. So you'll have exponential ix 1 over d squared. Then let's combine the i's. I can see there's I2d plus another I. That's the same as, or simply I can combine the d, those with the d only. This one. So you can just write plus I into 2d plus 1. Then I squared is -1, so that's -1. Operating on x. Alternatively, I could just have the coefficients of d operator written as this way. You could write this as exponential ix 1 over d squared plus the coefficients of d. Which ones are they? Here we have I2 plus 1. Those are the coefficients of d plus I minus 1. Still the same. And then this is operating on x. So x is a polynomial of degree 1. So that if you operate on a polynomial, remember, let's comment on this. This is a polynomial of degree 1. So we need to drop the higher powers of d that are greater than the degree of the polynomial. So we drop d squared. Remember here there was a plus d which I didn't write, so take note of that. There's a plus d. So what we remain with is 1 over that is d minus 1, then plus I times 2d plus 1 operating on x. So what do we do again? I need to get rid of the complex number from the denominator. So I need to multiply numerator and denominator by the conjugate of the denominator. There was exponential ix here. So this can as well be written as exponential ix. Then here we have d minus 1 minus I 2d plus 1 over, here we have d minus 1, that's a plus I 2d plus 1 by the conjugate, multiply by the conjugate, that is d minus 1 minus I 2d plus 1 operating on x. Let me write x properly. That should be x operating on x. So I need to work out the denominator. Open the bracket, the denominator, that is exponential ix. Numerator, we have d minus 1, and then minus I 2d plus 1 over, denominator is difference of two squares, that is d minus 1 squared minus I squared, so that would be plus, remember where this I is negative 1, I squared is negative 1, so you expect that to be plus 2d plus 1 squared. This should operate on x. What do we get when you expand the denominator? Let's see. Denominator will give us is d minus 1 squared plus 2d plus 1 squared. That's the same as d squared minus 2d plus 1 plus 4d squared plus 4d plus 1. And so this equals to 5d squared plus 2d plus 2. If you simplify, that's what you get. 5d squared plus, remember this and this, 5d squared, negative 2d plus 4d, that is plus 2d, and this other one is plus 2. So what I'll write here is exponential ix d minus 1 minus I 2d plus 1, everything over 5d squared plus 2d plus 2. And here we have x. Again, I can drop 5d squared because d squared, or simply the power 2 is greater than the degree of the polynomial. This is polynomial of degree 1. So 2 is greater than 1, so we drop the 5d squared. And now we have 2d plus 2. This can as well be written as 1 over 2 exponential ix. Then we have this d minus 1 minus I 2d plus 1 times 1 over 1 plus d operating on x. So what you do here is to expand this in Maclaurin series. So this one, expand in Maclaurin's series. When you expand it, what do you get? Let's see. We are going to have 1 over 2 exponential ix. Then here we have d minus 1 minus I 2d plus 1. When you expand that, you get 1 minus d squared plus, no, that's 1 minus d. Instead of d squared, that should be d. 1 minus d plus d squared plus so many other terms, that's I order terms, operating on x. So let's take x inside the first bracket. If you take it inside here, what do we get? It will be 1 over 2 exponential ix, then d minus 1 minus I 2d plus 1. Inside here we'll have x minus 1. 1 because derivative of x is 1, second derivative of x is 0. The higher order terms will evaluate to 0. So x minus 1 again, take it inside the bracket. Let me use another color. X minus 1, you take it inside this bracket so that you'll have 1 over 2 exponential ix. X minus 1 inside, this is what we are going to get. So we'll have d operating on x minus 1. Then there's minus 1 times x minus 1. Remember this one? Then there's minus I, the iota. Inside there we have 2d operating on x minus 1 plus 1 times x minus 1. There's a closing bracket and another bracket. So when you write d, the d there means derivative with respect to x. So that what we'll have here is, remember when you differentiate x minus 1 with respect to x, you get 1. So there we'll have 1. Again, here means that derivative of x minus 1, that is 1 times 2. So this is the same as 2 times 1, which is 2. So what we'll have here is now equal to 1 over 2 times exponential iota x times, here we'll have 1. Then now negative 1 times this bracket, we'll have negative x plus 1. Let's open the other bracket. So minus iota. Here we'll have 2. Then plus x minus 1. Of which, if I simplify this further, this is what I'm going to get. So it will give us 1 over 2 times exponential iota x times, so this will give us 2 minus x. And now we have minus iota times 1 plus x. 1 plus x. Remember, we can group this. This is the real part and the other one is the imaginary part. And remember, exponential iota x is the same as cos x plus I sine x. So we can replace that by its value of the identity. So that's the same as, I'll have there 1 over 2, so that here I have cosine of x plus I sine of x. This should multiply 2 minus x minus iota 1 plus x. And so we said we need to extract the real part. So when we extract the real part, we are going to get our particular integral. So I can write here that extract the real part. When you do so, you are going to get y subscript c, subscript p, I mean, to mean particular integral, is equals to. Now, what will give us the real part is when I multiply cos x times 2 minus x. Those will give us real part. So this is the same as 1 over 2 in bracket 2 minus x times cosine of x. Another one is when I multiply this one, iota sine x times this other complex, the iota, negative iota into 1 plus x. Because you know I squared is negative 1. So that means we'll have I sine x times negative I into 1 plus x. So that we'll have negative I squared, which is the same as positive 1. So that's the same as positive 1 plus x. And this should multiply sine x. So that's the real part, and that's our particular integral. Somebody might be asking, why are we extracting the real part? It's because on the right-hand side, our function was cosine. And I already explained that the Euler's identity is the same as exponential ix, which is the same as cos x plus I sin x. But we were only operating on cos x on the right-hand side, and cos x is the real part of that Euler's identity. And so that's why we are extracting the real part of our solution. So now the general solution is the sum of those two solutions. So you can just write here that general solution is simply equal to the sum of the complementary function plus the particular integral. Or you could write this as y is equals to yc plus yp. And so we can replace them. Let's check what we got as our yc. So we can go back and you realize that here we got c1 plus c2 exponential negative x. So that's what I write here. And then add to what we have found as our yp. So you can write or y is equals to c1 plus c2 times exponential negative x, then plus now what you found here is 1 over 2 times 2 minus x. Remember there's a bracket. Here we have cos x plus here now we have 1 plus x sine x. C1 and C2 are arbitrary constants which can be determined if you are given some initial conditions. But in this case, we have not been given the initial conditions, and so we cannot be able to find the values of C1 and C2. So that's our general solution. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving inverse differential operators. Bye bye.